In this example, a person is dropping a penny off of a building, and we want to know how fast is it going in the instant that it hits the ground. Well, once again, we have to figure out what we know and what needs to be determined. We know that the person is holding the penny before he releases it, so the initial velocity of the penny is 0 because it's not moving. The displacement of the penny will be 0.150 kilometers because that's how tall the building is. Now please note, as soon as I say displacement is 0.0150, I have made a determination that movement down is going to be considered positive movement because the penny is going to fall down 0.150 kilometers. So I've decided that I'm going to make down the positive direction. I could make down the negative direction, that would be fine. But if that were the case, the displacement would have to be negative 0.150 kilometers. But I'm going to stick with the idea that motion down is positive, so the displacement is 0.150 kilometers. We also know that the acceleration of the penny must be 9.8 meters per second squared because the penny is in free fall. Now remember, the acceleration is pointed downwards, and I've defined down as positive, so that's why acceleration is plus 9.8 meters per second squared. If I had said displacement was negative 0.150 kilometers, then acceleration would have to be negative 9.8 meters per second squared. I have to keep my direction consistent. In this case, down is positive, so displacement is positive and acceleration is positive. Alright, that's everything we know. The thing we need to figure out is the final velocity, v. Given what we know and what we need to find out, what equation should we use? Well, we need an equation that relates velocity, acceleration, and displacement. What about this one? V squared equals V naught squared plus 2a delta x. Now before we plug into this equation, we need to make the units consistent. Notice that displacement is in kilometers, while acceleration is in meters per second squared. To get the units consistent, let's convert 0.150 kilometers. I take that number and I put it over 1. Then I multiply by the conversion relationship. There are 1,000 meters in 1 kilometer. If kilometers are on the bottom, then kilometers cancel, leaving meters, and I'm left with 150 meters. Notice, however, that 0.150 has 3 significant figures, so I have to make my answer 3 significant figures as well. The only way to report 150 to 3 significant figures is 1.50 times 10 to the 2. Alright, well, I'll move that up so that that's the value for displacement now, 1.50 times 10 to the 2 meters. Now I can plug into the equation. V is what we're trying to figure out. V naught is 0. Acceleration is 9.8 meters per second squared. And displacement is 1.50 times 10 to the 2. So when I work those numbers out, I find out that V squared is 2940 meters squared per second squared. Once again, right now I'm just keeping all digits. I'll worry about significant figures in the end. To figure out what V is, I have to take the square root of both sides. When I take the square root of V squared, I just get V. When I take the square root of 2940, I get 54. I need to keep this to 2 significant figures because if I look at the original equation, 9.8 has 2 significant figures, 1.50 has 3. So my answer can only have 2 significant figures. So the penny hits the ground with the velocity of 54 meters per second.